So here we are with the first exercise of chapter 3. This one is about bar plots in pandas. So we start by generating a 4 by 3 matrix of numbers as a pandas data frame, and that should look something like this. So you can see we have 0, 1, 2, 3, 4, 5, and so on up to 11. And then you want to make two sets of bar plots, so visualize the data in two different ways, or both with bar plots, but oriented differently to highlight different features or different organization of the data. So here you can see bar plots where we are grouping the columns together. So there's a separate bunching or grouping for each row. And within each of these, I call categories, but it's just arbitrary numbers. You can see that the data come from each column. So this is the numerical values of row 0 are 0, 1, 2. So there's no blue bar here, but there kind of is a blue bar with a height of 0. And then the next grouping corresponds to the next row and so on. And then over here, we have basically exactly the same numbers, exactly the same data, but we're grouping in a different orientation. So here, each of these kind of bunches corresponds to a column, and then we are putting the rows together within each bunch. As I discussed in the chapter, neither one is correct or incorrect or better or worse. These are just used to highlight different features of the data. Of course, here it's all arbitrary. These are just meaningless numbers. Okay, so now let's switch to Python and I will show you my solution. So here you can see I'm using pandas, which I've already imported earlier in the code. Data frame, this function data frame, and I'm importing. Here is just a range of integers from 0 up to 11, and then I'm using numpy.reshape to reshape this vector into a 4 by 3 matrix. And that's how we get this data frame here. Of course, there's other ways to create this matrix. Any way you do it is fine, really. Okay, and here we get to the visualization in pandas. Now notice that we are not calling matplotlib.pyplot.barplot. Instead, we're using this general method on the data frame called plot.plot, and then we specify with an input what is the type of plot or the kind of plot that we are looking for. In this case, it's a bar plot. Now, notice, so I'll just run this code. So that creates the figure with these two different bar plots. Notice that both of these functions here, so this call creates this axis, this subplot, and this call creates this subplot. Now, both of these are basically identical. They really are identical, except for the reference to the axis. So what differs is this method .t here, which stands for transpose, and it takes the data matrix oriented like this to a data matrix oriented like this. And actually, I'll even show this to you here. So here you see what the data frame looks like. And now if I transpose it, that's just swapping the rows and the columns, and therefore also the columns turn into rows. So this is the easiest way to swap the organization of the visualization using pandas. The goal of this exercise is basically to produce this figure. I have quite a few exercises throughout this book where the purpose of the exercise is really just to reproduce a figure. There are two purposes behind this, two motivations for this exercise. One is to give you a little bit more experience with creating data visualizations in matplotlib, in particular bar plots and error bar plots, and also to translate mathematical formulas into code. It's an important skill for anyone working with data or applied mathematics. Okay, so this is the figure. Let's switch to the text. So here's the text of this exercise. And it basically just says create a data matrix containing 30 observations and 6 features. So this is a 30 by 6 matrix. And here is basically the set of formulas for how we create the data. So the data are random numbers drawn from a normal distribution, but that normal distribution is different for each column of the data matrix. So I here refers to the ith column of data matrix Y. So it's random numbers distributed as a normal distribution or drawn from a normal distribution with a theoretical mean of mu, and that mu is defined here. and a variance of sigma squared. So here is where I define mu, so that's pretty straightforward. That's just going to increase as a function of the column number. And here, notice I'm not actually defining the variance, I'm defining the standard deviation. And the variance, of course, is the standard deviation squared. So some weird looking formula. I don't know how I came up with this, just playing around with some numbers. So 30 times 2i divided by 5. Again, I is the column index. And then the rest of the text of this exercise is not that interesting. It's basically just explaining what I've already explained. So let's switch to Python, and I will show you my solution. So here I define the parameters, and here, so in the math expression, I call this capital Y, and here I'm calling it variable data. You could also call this Y if you prefer. So I initialize this to be zeros, a matrix of zeros, and then we loop through the rows. And now here I'm saying that there's two ways to implement this. This line here is a more direct implementation of the expression that I showed in the book, in the text. So in particular, this function here will generate random numbers normally distributed with a mean of 0, a theoretical mean of 0, and a theoretical variance of 1. And then I'm modulating that. So you can see I'm adding. So I'm adding to that a mean offset. So this is the mu per column. And here, this is the variance. So I made it a little bit confusing here because I'm splitting up the standard deviation. I'm splitting up the standard deviation equation or expression into different parts of this line of code. So here's the 30 times, and then over here we have 2i divided by, now in the formula I showed 5, but here I'm writing it as n minus 1. This actually corresponds to the number of columns, so this still ends up being 5. Minus 1 squared. Okay, that's one way to do it. You can also specify mu and sigma directly as input parameters to the function numpy.random.normal. So both this line and this line will give you the same result. It all really depends on what you feel more comfortable with. Okay, so we can run that line of code or that cell. And then, yeah, here we're creating the figures. So here I say the naked bars. So this is just the bars without the error bars. So I'm only specifying numbers from 0 to n, or n minus 1. And then the average. Now, because this variable data corresponds to a matrix, we need to specify the axis. Otherwise, Python or NumPy is going to compute the average of the entire matrix. So all the elements in the matrix, which is not what we want. We want just the average separately for each column. Okay, this is just some plotting adjustments. So then here in the middle axis plot, I'm creating just an error bar. And yeah, so you can see, so I have the x-axis coordinates, and then I'm plotting the mean and the standard deviation. And then here on the right plot, we have a bar plot and then an error bar on top of that. So, so to create an error bar, I'll run this code. To create an error bar, you actually use first a bar plot and then the error function. Exercise 3 is about implementing pie charts in Python. So the question provides this little data set here. This is fake data. Basically, I pretended that I asked a bunch of people about their favorite ice cream flavor. So you can think about which is yours from this list. And yeah, the idea is first we are supposed to ponder whether these data are even appropriate for a pie chart. And then, assuming they are, then we visualize and try to get our plot to look something like this, where we have different colors and we have the labels and the percentages, and some of the pieces of the pie are like popping out here. Okay, so as for the first question, obviously the answer is yes, that these data are appropriate for a pie chart. The answer is obvious because if the answer were no, then I wouldn't have written this question and we wouldn't have this beautiful result here. But the important question is why are these data appropriate for a pie chart? And the answer is that they all sum up to 100%. Now, these numbers do not sum to 100. These are counts. So in order to be able to visualize these data using a pie chart, it is necessary to convert these data from numbers, from counts, into a proportion or a percentage. And that's what you see here. So that's why chocolate here is listed as 24. This is 24 people said chocolate is their favorite flavor of ice cream, and that corresponds to 38.1%. Okay, so now I will switch to Python and show you how I implemented this exercise in code. So I wrote this data set out as a dictionary. You can use a dictionary, you can use a pandas data frame. In principle, you can also use a NumPy array or a list, but plt.py, so the matplotlib function to create a pie chart, works really well with dictionaries. So that's how I created this dictionary. So the inputs into this function plt.py are the values, which are the numbers. The labels are the keys of this dictionary. And then there's an optional input called explode, which refers to how far out these pieces are from the center. So this goes in proportion. So this is 0%, which means that piece of the pie is all the way like fitting inside the pie. 10% blown out, 0, and then 15% blown out. And then the radius refers to the label. So that's how far out the labels are from the center. And this is normalized units. So this would be basically 20% bigger than the radius of the pie chart. And then here, this is auto percent. So it turns out that the function pi will automatically convert the data from whatever numerical values you input into percent for you. So you don't need to do that manually. And then here, this is just listing a formatting. So it's 0.1. F means that it's going to give one decimal point or one number after the decimal point. Okay, this commented code here is just to illustrate that you can also do this manually. You can also manually convert the data from numbers into percentages. And basically that's what this code does here. Okay, so we can run this code and we see this nice looking pie chart. Of course, you can change a lot of other things. You can change the color palette that's used here, all sorts of little things that you can change to your preferences. There are several learning objectives in this exercise. One is to use NumPy's histogram function, so you can get the actual values of a histogram instead of just creating a histogram plot. Another one is working more with the boundaries of the histogram bins instead of the centers. And what was another one? Oh, yeah, converting from counts to percentages. Okay, so lots of exciting things going on in this exercise. The basic goal of this exercise is to reproduce this figure here. So what are we looking at? Well, you see two histograms, and it's also pretty clear that these are same histograms. So it's the same data in both of these panels. The difference is only in the y-axis scaling. Here in panel A, we have counts. Here in panel A, we have percentage. So I've normalized the data from counts into percentage, which is the same thing as proportion multiplied by 100. And then, here in the title, I'm summing over all of the y-axis values for all the bins. And here it's sums to 500, and here it sums to 100. Now here it sums to 100 because these are percentages, so they should all sum to 100. Why is this summing to 500? What is 500? Well, it's kind of an arbitrary number. That's basically just how I set up the instructions. So I say, randomly draw 500 numbers from a gamma distribution, and you can access the gamma distribution using NumPy's random.gamma function. And there's two parameters of a gamma distribution, scale and shape. And for simplicity, we can set these both to 1. Okay, so now instead of using the matplotlib hist function, we should use the NumPy's histogram function. And that's going to give us out the x and y axis values without actually generating the plot. So then we will have to use matplotlib to draw the plot. Okay, and then, convert from counts to percentages. So now I will switch to Python. I'll walk you through my solution. Here I'm generating the gamma or the data drawn from a gamma distribution. Here's the two parameters and of size 500. Okay, so here is part of the key piece of this code. So instead of using matplotlib to generate a hist function using, for example, plt.hist, instead I'm using numpy.histogram. I input the data, And the number of bins, how to decide for the number of bins to use, is a little bit arbitrary. There's really no reason why you couldn't use 39 or any other number. I'm going to talk more about this later on in the book. This provides two outputs, y and x. Y are the heights of all the bins, and x is the boundaries of the bins. Now, before going through any of the rest of this code, I'm going to comment this out and run this code. I just want to show you what these outputs look like. So here is actually, I'll start like this. So let's just look at x and y. So you can see x is floating point numbers, y is integers. So these correspond to the heights in counts, and these correspond to the bin boundaries, which means the start and stop of each bin. And that means that we have, if you look at the lengths of these two, here they're the same length, because I also wanted to come out that line. Okay, now we see that they are different lengths. So x is 41 elements long, and y is 40 elements long. And that means if we were just to try to plot x by y, we'd get an error message because the shapes don't match. Okay, so y is, what is going on here? What's going on here is that x here, this second output of the NumPy histogram function, actually gives us the lower and the upper boundaries of each bin. Now, because all of these bins are neighbors, all of their boundaries touch. They all share the inner bins, and then there's an extra pair of boundaries at the ends. So to make a plot, what you want to do is get the bin centers. And so how do you get the centers of the bin when you already know the boundaries of the bin? Well, the centers of the bin is obviously just the average of the boundaries of each bin. And that's why I have this code here. So we take elements from 0 to n minus 1 plus elements 1 to n, and that's the sum of the two boundaries, and then we divide by 2 to give the average. Okay, and then here is another piece of this exercise where we normalize to percent. So this is also very simple. Mathematically, it's very straightforward, but good to get some practice and internalize this. So you just divide each of the bin values by the sum over all of the values in all the bins. And then, you can optionally multiply by 100 to convert from proportion. So this would be proportion, and here we have percent. After that, it's just some pretty straightforward plotting commands, nothing terribly difficult here. In a purist statistical data visualization world, you should never use lines to visualize a histogram. You should only use bars or maybe dots or something like that, but not drawing lines between them. Now, that is the purist view, and I don't entirely disagree with that view, but we also live in the real world, and in the real world, you sometimes have to make sacrifices or different choices in order to optimize some other priorities. And sometimes you have a priority to display multiple pieces of data or multiple different features of data or different data sets in the same graph. And using bars can be difficult for that kind of application, where using lines might facilitate visual interpretation. So therefore, my argument in this book, which many other people argue, though not everyone, is that it's okay to use lines in certain cases, like when it really facilitates visualization. And so introducing you to this distinction and making this decision is the main goal of this exercise. So this exercise 5 in chapter 3. So what you want to do is basically just create a plot that looks like this. Here we see histograms of exactly the same data drawn with bars or with lines. So where do these two data sets come from? These are numbers that are randomly drawn from either a normal distribution or an exponential distribution. So here this is normally distributed numbers with a population mean of 2 and a variance of 1. I call this G for Gaussian. This is E for exponential. Here you take a standard normal distribution and then you input it into the natural exponential function. So you can use n of 200. And then basically what you want to do is create panel A over here using matplotlib hist function, and panel B using numpy.histogram to get lines very similar to what we did in the previous exercise. And now what I want you to do here, this is a little bit of a trick in Python, or something that is handy to know about, is to create use exactly the same bins for both data sets. So that means that the bins boundaries is exactly the same for both of these data sets. Now that doesn't just happen magically. You're going to have to figure out a way to do that. Okay, so then finally, here I just say make a determination, and then finally try it again, this time using 5,000 data points instead of 200, and use 100 bins instead of 30. So basically just running the same code again, changing a few parameters. Okay, I hope that makes sense. Now I will switch to Python and show you my solution. So here you can see I'm creating the data. It is 200 data points drawn from a standard normal distribution, which I then shift by 2. Here I take a standard normal distribution and input that into a natural exponential function. Okay, so now to define the bins, I take linearly spaced numbers between the smallest number and the largest number. Okay, so, and then that is coming from the combination of both data sets. So basically I take both of these data sets, I put them together, I find the smallest value and the largest value, and I generate linearly spaced numbers between them. And that is how I will define the bin boundaries. Here I say k plus 1. You remember I had this discussion in the book, but also in the previous video, that these bins here, this parameter for bins, this is the number of bins if you input a number like 40, or it is the boundaries of those bins. And so if we want to specify the boundaries, then we need to have k plus 1 numbers for k boundaries, k bins. Okay, so you can see that, this is the same line of code, but for dataset 1 and dataset 2, using the same bin boundaries in both cases. Okay, so let's see what this looks like. Well, it looks very similar to the figure that I showed in the book. Okay, now for two histograms, it's okay to overlay two different histograms on top of each other using bars. That's still relatively visual. In my opinion, lines look a little bit better. The more conditions you have, like if we would have, let's say, 5 different data sets to compare in the same plot, using bars, it really just doesn't work anymore. You have to switch to lines. Now, the issue with using lines, as I discussed in the book, is that when you draw lines in a plot, you are implicitly assuming that you know that the data value between, this value and this value. Actually, let me draw these again with markers. Let's see, I'll do like this line, and let's do squares for this one. Okay, so the issue with lines is that when you draw a line on the plot, you are making the assumption that the value between, this bin and this bin, like between, this is about 0, this is about 0.2. You're saying that, the value at 0.1 is going to be 20. Is that reasonable? I mean, this histogram is pretty smooth, so I don't think it's so unreasonable, but that is just an assumption that you are imposing on the graph by drawing lines, and that is an assumption. It's not really based on reality. Okay, so therefore, the idea is that the denser your histogram, the more histogram bins you have, the more appropriate, or maybe I should say, the less inappropriate it is to use lines connecting the different dots, the different bin centers. Now, there's another, there's always a balance with all these things. If we would specify 100 bins with a sample size of 200, that is technically possible, but that also is not going to be really, okay, actually here it kind of works out well because most of the data are clustered at these smaller values, but you can still see, there's a pretty big gap between these 2 points here. So the larger the sample size, maybe I can make this more extreme. Let's do 40. Okay, I mean, this is really ridiculous to have 40 numbers. So here, you really can't see anything, but this is not a very good histogram either. Okay, so let me see. I think I specified 5,000 in the text. So now you see this looks a lot smoother. You still get a bit of a gap here, but I think lines are more appropriate here. And again, in my opinion, lines really help us visualize the two different histograms here, especially how they differ and how they overlap. Here we are in exercise 6 of chapter 3. The goal of this exercise is to compare linear versus logarithmic scaling for plots. And as I discussed in the book, the difference is that linear scaling is based on addition. So you can see each of the successive tick marks each of the equidistant tick marks are defined by addition. So you take this tick mark and add 20, and then add 20, and add 20, and add 20, and add 20. Here, with a logarithmically scaled plot, the tick marks are based on multiplication and not on addition. So this tick mark is 10 times this is 10 times this, 10 times this, 10 times this, and so on. So what you want to do in this exercise is create these two functions, y equals x and y equals e to the x. And here you see the values I'm using. So x goes from 0 to 6. E to the x grows really fast. It's even off the charts by around like 4.5 or so. It's not even visible on this axis anymore. Okay, so then we have exactly the same data in both of these panels. The only difference is it's not the lines, it's not the data. The only difference is the y-axis scaling. So linear scale and logarithmic scale. And it's really striking to see how these two functions look different, even though they are exactly the same numbers. And so, so try this and then make some observations, which I will discuss in Python. And then here, the last part is to use minus x instead of plus x. So basically just to recreate these plots, but say y equals minus x and y equals e to the minus x. Okay, so now I will switch to Python and show you my solution and have a little bit of a discussion about when to use each of these different types of plots. Coding-wise, this exercise is relatively straightforward. It's mostly just writing code to visualize. Okay, so we have our variable x. This is linearly spaced numbers between 0 and 6. I never said how many points, so you can choose how many points you want. I did 1,001. Okay, and then basically I set this up in a for loop. Here's really the key thing here. So we have x and x, and then we have x and e to the x. So it's just that simple. And then, this is just in a for loop here, obviously, because we want one of them to be logarithmically scaled and the other one to be linearly scaled. In fact, the way that I've really set up this code is that it draws both of them identically. So this is creating exactly the same two plots. And then with this extra piece of code here, I just set the y-axis limit of the first plot. That's just because this linear plot here, this function here just looks like a flat line. So just changing the y-axis. Here is the key line. So I'm setting the second plot to have a logarithmic scaling. So here we see the results, which look the same as what I showed in the book figure. Not surprising there. So the question is, how do you interpret these and when do you use linear versus logarithmic scaling? Now, the thing is that most people who look at graphs, including trained scientists, are more used to looking at linear plots than logarithmic plots. And that's just because, we have so much experience in life looking at linearly scaled plots, even from when you're a kid. Like the very first plots you see in your life are always linear scaling. So logarithmic scaling is a little bit harder to interpret, because this is a straight line, but it's actually a nonlinear function. This is a curved line, but this is a curved line representing a linear function. So it's just a little bit confusing. It takes a little bit longer. So my advice is use a linear plot when it's possible, when the data are appropriate. Logarithmic scaling is appropriate usually for growth and decay functions. So you see this a lot in biology, in physics, in finance as well. If you look at long-term growth of the stock market, for example, you see it looks extremely different, linear and logarithmic. If you put it in a linear scale, it looks unsustainably crazy. But if you plot, the past 150 years of stock market developments and indices in logarithmic scale, it kind of looks like this. I mean, it's not that flat, but it looks like just a linear increase because it's something that's naturally growing. Okay, yeah, so growth and decay functions are often shown in logarithmic scaling. Okay, so then the last thing I want to do here is change this plot. Okay, so here I just changed x or the y values to minus. And then we can see what this does in the plot. And what it does is, okay, so this plot looks empty. Let me just comment out this line. So here on the right, we see this plot looks fine. We could change the axis scaling here, but this looks okay. Here we don't see anything and we get a warning message. And basically what's happening here is Python is trying to take the log of negative numbers, which do not exist in the real domain. They do exist in the complex domain, but we're not working with complex numbers here. So yeah, basically the warning is if you're plotting something in logarithmic scaling, you basically just want to limit that to positive valued data. So if the data are positive valued, then you can choose whether to use a linear or a logarithmic scale. If the data are positive and negative valued, or also if you have values equal to 0, then you can put in some kind of adjustment, some kind of transformation to make the data all positive valued, or just stick to linear axes. Exercise 7 of chapter 3 is all about violin plots and symmetric and asymmetric violin plots. So what you want to do is generate two data sets. One is uniformly distributed random numbers, and one is normally distributed random numbers. Store them in a pandas data frame in 2 columns. So you can imagine, I don't know, maybe these are paired data. You're going to run a correlation analysis with them. And then what you want to do here is generate a violin plot of each data column separately. So this is a violin plot of the normal distribution, and this is for the uniform distribution. And then you can see I've also drawn these dots on top. So this is not, the dots don't come natively from a violin plot. Like this, you don't see the dots here. So you can figure out something to do with Matplotlib, or I don't know, maybe using the Seaborn library, for example, to get these dots to draw on top. These are beautiful visualizations, by the way. As I mentioned in the book at the end of this chapter, this is a perfect example of where color would be great. You can use color here, make these plots really, really beautiful. But just because I printed this book in black and white or in grayscale, so here I just use grayscale. Anyway, you can see these violin plots are symmetric. They look the same on the left and the right. Now, if you have two data sets that you want to compare, you can draw an asymmetric violin plot, and that looks like this. So here we have the normal distribution on the left and the uniform distribution on the right. So, getting this, this is quite challenging, actually. There's a weird Python hack that you have to do to get this to work. If you're struggling with this part, then don't worry about it. I have the code in the solution file online. I'll show it to you in a moment. It's useful code to have. If you are trying to figure out how to do this on your own without looking at my code, then good luck. I hope you figure it out. If you don't, if you really struggle with it, don't worry. Just feel free to just look at my code and copy from there. Okay, so now I will switch to Python. Here I start by creating this data frame. It is, normal random numbers and uniform random numbers, 123 of each of those, because why not? Seems like a good number. And here's the column labels. So we have the norm and unif for uniform. Okay, so now here, actually, let me show you before I run too much of this. Actually, no, that's okay. I'll just run this. Okay, so I use two functions here, violin plot and strip plot. Violin plot obviously creates the violin plot. Strip plot is what creates all of the dots. And you can see I'm specifying the color palette to be dark :W, which basically just gives us black and white dots over here. Okay, so then the question is, how do we create this thing? And to do this, I want to start by just showing you these data frames. So this one is called df_all. Okay, so we have the data frame that I originally created. So you can see that that's 123 rows. There's two columns for normal distributed data and uniform distributed data. Now, the trick to getting this to work, to creating these asymmetric violin plots, is to um, reshape the data. So now I have a data frame which has basically one column of data, and that is all the numbers. And then another column with, it's just called distribution, but this is just a label that is either norm or uniform. So basically, I've just collapsed this data frame from having two columns of data into one column of data. You can see the concat method here will concatenate these into one axis. Okay, and then we need to create another column for the data type label. And then use the same plot, so violin plot, but here we can split the data according to, Python calls this input option hue, but it's according to the distr. So it's the column called distr distribution that Python will use to split the data into these two halves like this. So there you go. Now you know how to create violin plots with dots on them and also asymmetric violin plots. These are great, but just keep in mind that violin plots only, asymmetric violin plots only really make sense if the two data sets are in a roughly comparable range. You can imagine what would happen. Actually, let's just try it, just to have some fun. Okay, let's see if I would say 10 plus. So I'm just adding an offset to this. Okay, so now this is already, this plot I think is already kind of difficult to interpret, but you still get the idea. But this one just looks really weird, I think. So yeah, for an asymmetric violin plot, it's useful to have data sets that are in roughly comparable numerical ranges. So here we are with exercise 8 of chapter 3. The goal here is to use the Plotly library to create figure 3.25. I'll show you this figure in a moment so you can see what it looks like. Now here I say, if you are not already familiar with Plotly, you might have to look up online how to work with this library. Now, I do this occasionally in exercises in my books, in my courses, in my YouTube videos, basically where I say, here is a function that you use. I'm not going to tell you how to use the function. You might need to search online. Now, occasionally, most people seem to be fine with this strategy. Occasionally, I do get some learners who are annoyed. They find this unpleasant or even unacceptable because they think that, you know, they should learn, I should be able to teach them everything that I want them to do. On the one hand, I totally sympathize with that sentiment. You are investing your time and possibly also your money or maybe someone else's money into this book. So shouldn't I tell you everything? But, the flip side of that argument is I don't think it really benefits you if I just spoon feed you everything. So learning does require some effort. It requires some exertion and some time. And so searching online is just a very, very real part of using Python. You can read a million books on Python and statistics, and you will still end up needing to search for things online or look things up on, ChatGPT or some other AI. Anyway, so use the Plotly library to create figure 325. Let's have a look at this figure. Here is figure 325. It is a radial plot, or it's sometimes called a spider plot, which shows the high temperatures near Patagonia as a function of months. So this is a beautiful way of illustrating data that are naturally circular, right? These data are circular because we go through the year from January to December and then back to January. So it cycles through. Time is like this. Phase is like this if you're doing spectral analyses or time frequency analyses. Clocks obviously are like this. Not all kinds of data are amenable to these kinds of visualizations. And I give another example in the book here. There's nothing in between sci-fi and rom-com, romantic comedies, so it doesn't make sense to have a line here. And to me, it doesn't make sense to have a visualization like this because you don't cycle through these movie genres and end up back at sci-fi, for example. Okay, but anyway, the data and the link to the data are in the online code, so you can copy that or you can just eyeball this and approximate it. The exact numbers don't matter here. It's more about just learning how to work with a different library to produce a visualization like this. So here we are in Python. This is the link to where the actual data come from. As I mentioned, you can just look at the figure in the book and approximate these numbers. It doesn't really matter. Here's all of the years. And yeah, here's where I put them into a data frame. And now using Plotly is actually really straightforward. I mean, it's not something you could just guess and use correctly without looking up online. But I think it wouldn't take you more than a few minutes of your life to learn how to use the Plotly function to make these polar line plots. Pretty straightforward. You just input the data frame. You have to specify theta, which is the angle, and that is month. That's just the variable name that I chose here. And R stands for radius. That's the distance away from the origin. And here I say temp, and that's because I called this column label temp in the data frame. Okay, and then, yeah, basically you just run that plot here. And then, yeah, if you get there's just a note here. If you get this warning message here, don't worry about it. If this starts to cause errors, I will actually change the code. Otherwise, there's nothing wrong here. It's just a warning. Okay, so here we get this nice looking plot. It's a little bit different from the exact plot that I showed in the book, and that's basically just because Plotly is a different library with different visualization options, and yeah, lots of nice little tricks like this. You can zoom in to certain parts of the graph. Okay, now I'm starting to lose it. But anyway, Plotly is, in general, a pretty nice library. It does lots of things like animations as well. So it's something you can consider checking out.